our topic is about motif counting on uncertain graphs. First, graph analytics are prevalent in different domains, such as network comparison and protein function discovery in biological networks, and also studying the transitivity properties and community detection in social networks. In the above applications, motifs are typically involved. For motifs, it means small graphs with a few nodes and edges. It is also regarded as a building block of a larger graph. Here we give some examples of the 3-node and 4-node motifs. For motif counts usually reveal interesting properties of a graph G. For example, the larger triangle count of a graph, it means that this graph is closer to being transitive. Also, the global clustering coefficient can be computed from the 2-star count and the triangle count, which can be used to discover the topological and functional properties of the protein-protein interaction networks. Here we give the definition of the motif and the motif instances. First, we define a graph G as a pair of V and E. And also a motif M is a connected graph. A motif instance of M in G is an induced subgraph in G, which is isomorphic to M. By isomorphic, we mean that there exists a bijection from Vm to Vs, such that for each edge in Em, there is a corresponding edge in Es. For each edge in Es, there is a corresponding edge in Em. The subgraph induced by ABC is a motif instance of a triangle. In the above applications, the graphs are not always deterministic. For example, the existence of an edge is based on experimental results in the protein-protein interaction networks, which can be erroneous. And some edges between the users are predicted in social networks. Further, the uncertainty is inherent in the wireless and sensor networks. Here we give the definition of the uncertain graph. Uncertain graph is defined as a pair of G and P. G is the deterministic graph. We also call it the backbone graph. And P assign each edge a probability to exist. Here we follow the possible word semantics. It means for each graph G, it can be treated as the set of all possible deterministic graphs. In this small example, the edge BC and the edge DE have a probability of 0.5 to exist. Thus, it can have 4 possible graphs according to the status of edge BC and edge DE. Here we give the formal definition. Because the motif count of M in the uncertain graph G is a random variable, thus our goal is to evaluate the occurrence statistics of M in G. Is PMF, mean, and variance. Here we give a small example of the PMF. In the literature, the motif counting is extensively studied in the deterministic graphs. People start from the triangle count, and then they further study the 3-node and 4-node motifs, 5-node motifs, and they also use the approximation algorithm to further speed up. In the uncertain graphs, the motif counting only have few works. The state-of-the-art one is the ACM BCB50. It calculates the mean and variance of the count of a given motif, which is quite similar to our problem definition. For the BME method, to calculate the variance of the motif count, it needs to enumerate all other motif instances which share common edge with this motif instance for each motif instance, which means in the worst case, the time complexity of this algorithm is the square of the motif count in the backbone graph G, which is very time consuming. Thus, we developed the two sampling based method to improve the efficiency and also keep the high quality of the result. The first algorithm is the possible graph sampling. We first samples and randomly chosen possible words from the uncertain graph, and for each possible word, a deterministic motif counting algorithm is used to compute the motif counts. And then we aggregate the motif count on the n samples to get the PMF mean and variance. The PGS can still be time consuming because the motif counting process is repeated on each sample, while the samples may share some common paths. So we introduce an interesting finding that the two successively sampled possible words tend to be similar to each other, which means the expected relative edge change over the two samples tends to be small. Here, the expectation of the number of the edge changed from one sample to the next one compared to the number of odd edges is less or equal than 0.5. Based on this finding, we developed a new algorithm, LINC. It contains two stages, linking stage and counting stage. In the linking stage, we find all motif instances in the backbone graph G, and then we build a linking table on each related edge, containing the relationships between the weighted edge and the motif instances. In the counting phase, we randomly sampled n possible graphs from G, and for each sample, we incrementally update its motif count based on the count in the previous one with the help of the L table we built in the first phase. Here we give an example to show how we update count from one sample to the next sample. In this small graph, the edge E1 disappears. That's because there is a new rectangle appears, BCEF, that's the number +1. Next, edge E2 appears. There is no new rectangle appears, or existing rectangle disappears. Thus, the number remains the same. In total, the number increased by 1. We also have other optimizations. So we encode the motif instances into the bit string to save the space and also speed up the motif instance comparison. And we use the early stop strategy to further improve the efficiency of our algorithms. And we also try to avoid some indexing some motif instances to save the space. In the experiment part, to evaluate the effectiveness of the algorithm, we evaluate the relative error of the estimated variance. From the result, we can see that our algorithm can always provide a high quality result with the relative error within 5%, which is much better than the baseline method. For the efficiency part, our LINC algorithm is up to 1,000 times faster than the baseline method. Yeah, that's all. Thank you.